Okay, so the first thing you need to know about the device side of the software is what is actually happening in the run script. So if we open up run.sh, we can see that we're setting our virtual environment, capturing a few command line arguments, and then really the main thing that's happening is we're running python manage.py run server locally at port 8000. So this is invoking the Django application. So if we go into this app for just a second and we open up this apps.py file, this file is ran very early on in the Django process. What we're using this file to do is to create an instance of our coordinator manager. So the coordinator is what's ultimately will spawn all of the other manager threads. So this is the spawning of the coordinator thread. So if we pop back up into device, we can see all of the different managers, the coordinator, the IoT, the network, recipe, resource, and upgrade, as well as the controllers and the peripherals. So I use manager as a way to represent an instance of a state machine that's running as its own thread. Outside of that, I consider it a utility, and this is a script that doesn't necessarily fit within the scope of the manager instance, or is a general purpose tool that could be applied to a number of different places. So let's open up the coordinator, since that's what kicks everything else off. You can see there's events. This defines the different events that the manager can receive, so it can be reset, shut down, or loaded device configuration. You can see the different modes. These are the modes that the state machine must be in, and if it transitions from an unexpected state that hasn't been predefined from the beginning, it will enter into this invalid mode. So let's open up the manager, and here we can see that the manager inherits from the state machine manager. So let's just go ahead and open that one up to see what is happening first. And again, this isn't a manager instance, it's more of the manager type, so it's located in the utilities folder. So if we open up our state machine manager, we can see that it initializes the logger, sets the threading, event queuing, and initializes some of the transitions. Outside of that, it can be spawned as a thread daemon. This is important because it needs to run as a background process and not block, so we can spawn the other threads. The next thing it's doing, this is pretty important, it's the run function. This is always executing to make sure that the state machine transitions from one mode to another. So initialization mode, this is really like a quick function that'll just instantiate something new or initialize a config. If there's something that takes a bit longer, something like a CO2 sensor that takes a long time to warm up, that would go in a setup mode, and we could just add in a new mode and say, all right, modes.setup, then go up to the top and say, all right, our transitions, modes.setup can transition to these possible valid modes. And you'll see that in some of the other peripheral managers. And then in normal mode, it's basically going to be executing whatever is normal for it. So if it's a sensor, that's something like reading the temperature. An actuator is checking its control set point, and if its desired state should be on or off or somewhere in between, it'll do that, and as well as check for new events. So in the device UI, when we saw enabling manual mode for the peripherals, that is an example of an event that will be checked for in this moment. The same thing with turning on a light panel or turning off a light panel. And of course, there's a reset and an error mode if something goes wrong, and it can be shut down. So these are just these functions for transitions are just making sure that the transitions are valid, so we don't end up in a weird state like I mentioned. And these are the event creation functions and event check functions that really just run these helper scripts to make sure that the behavior does what we expect it to do. So if we pop out of here, and go back to our coordinator manager. I believe we still have that open. Yep. We can see that one of the very first things it does is it initializes state. So this concept of shared state is pretty important. It's really how all of the threads communicate with each other. So there's one single state object that is passed to every single manager. And because this is the same state object and we are running a multi-threaded application, it's important to lock the thread anytime we're accessing state. So if two managers running in different threads try to access state at the same time, we're going to have problems, and it's going to be no fun to debug. So always be careful when you're setting state, and make sure to use the thread lock. So for this one, we initialize our transitions, which we've already talked about. Maybe now is a good time to mention a decorator. A decorator is just a really convenient way to set or get, and it can do a lot more than just set or get, but for most of the purposes, as you'll see them, they're really just fancy setters and getters. So they're called each time you set a value to it. So on the set function, if we say, hey, self.config uuid equals XYZ, it's going to run this function and pass the value to it. And so I just use this as a nice way to always make sure that I'm locking state when I want to update my config uuid. And the same thing from reading it. I mean, reading it is doing the same thing, but it's just not passing a parameter. It's getting the parameter from the shared state object. And then we get to our run script, and these are all the different modes that we can have for our coordinator. It initializes, and then we're in a config mode, and in the config mode we're trying to read the config file, and we need to know what's in the config file, because at the point where we're creating and spawning all of our managers, we need to know how to create our peripherals and controllers, because they're configured dynamically. So we'll touch on how that's actually done in a minute, and you'll see these setup files inside each of the peripherals and controllers, and that's really the magic of how we're able to instantiate these on the fly. So once all of our standard managers and peripheral and controller managers are instantiated, we go into normal mode, and this is mostly just maintaining and storing the environment periodically, checking for new events and transitions, etc. And that's really all the coordinator does. So if we jump into, I guess, the peripherals, that's probably the next most interesting one. We see this is a little bit more complicated than the coordinator. There's classes, common, modules, and utilities. And that's because peripherals are a bit more complicated. There's a lot more peripheral types, and I've tried to write this without repeating the same code too many times, so there is some inheritance going on, and that makes it a little bit more complicated to get at first, but if you want to make a change, it's pretty easy to just do that from a single module versus changing every single one. So there is the peripheral base class that we can look at here. Let's see, peripheral, okay. And this follows the same pattern that we just saw, that all our state machine managers are going to follow. And we look at this, and this is nice because it sets default sampling intervals, update times, update intervals, etc. Pulls out all the configuration stuff so that we don't have to do it in every single file. So since almost all of our peripherals communicate over I2C, with the exception of USB cameras or the USB to I2C mux, USB to I2C dongle that we're using when we're on a laptop, they're all communicating over I2C. So what this is doing is initializing all these parameters, and based on what platform configuration we're using, it'll get the default I2C bus, mux address, etc. And then these are just the decorators that I've talked about for accessing shared state and running the initialization modes, setup modes, normal modes, calibration modes, etc. So if we go to a specific instance of a peripheral, I guess one thing to note is we do have a class for Atlas, but that's just because we have a lot of Atlas sensors, and I got tired of writing the same functions over and over again, so I've just moved it up and put it into a parent class that they all inherit from. So, okay, maybe we should mention common. Common are things like DACs or I/O expanders that aren't necessarily linked to a specific peripheral, but can be used among them. So a good example of what the DAC can be used for, and remember, a DAC is a digital to analog converter. So we send it a command over I²C, and we can set what the voltage output is going to be. So we can set it at 1 volt, we can set it at 2 volts, or we can set it at 3.3 volts, or anywhere in between that range. The DAC is really nice for setting that kind of a floating point voltage, if you will. So what we can use the DAC for is dimming light panels, and that's what we are using it for. But we can also use it to control relays. So we can send the signal to the relays control port and enable it or disable it. So that's the reason it's in the common instead of just the modules, because it is a common resource that all of the modules will use, or some of the modules, multiple modules can use. That's a better way to say that. So we have all of our sensors and actuators here. Lots of Atlas for CO2, dissolved oxygen, electrical conductivity, pH, temperature, CO2 sensor, LED panel, temperature humidity sensor, another CO2 sensor, and a USB camera. Just a general case actuator that can turn on and off via the I/O expander. So let's jump into the SHT25. And whenever I'm making a new driver, I always like to start with something that's familiar. So something like the SHT25 is a fairly straightforward sensor, and it's a nice place to start. So I'll just copy SHT25 and update the files as needed if I need to make something to support a new another temperature sensor or a sensor that just isn't supported yet. So if we dig into this for a minute, we can see there's the driver, there's the manager, there's a simulator, and a scripts directory, the setups, and the tests. So a good point to understand about this repo is all of the tests are at a per module basis instead of being in a mirror repository sort of structure. I guess a mirror directory. So there's two thoughts on how to make tests. One is you put them in module, two is you put them all in the mirror directory. I like them in the individual module because this code tends to be refactored a fair amount, and moving the tests around and keeping them at a per module level really just helps with that. Also, since we can go in and run these scripts individually, it's nice to have the tests close by so that we can make sure that it's working, the software is working in simulation before we have to question our sanity with whether or not the hardware is having a bug or the software is having a bug. So let's open up the driver. So it's fairly straightforward. It's initialized. There is an I2C lock. I mentioned a few minutes ago about having to lock the thread each time we access state. We have to do the same thing with the I²C bus because it is a shared resource, and if we have multiple threads trying to push bytes and get bytes from this resource at the same time, we're going to end up in this weird state, and it's going to break a lot of our stuff. So it's very important to always use the same I²C lock whenever you're interacting with I²C. Fortunately, this is all handled in the I²C communication module for you, so you probably won't have to worry about it, but it's just something good to keep in mind. So first we initialize our I²C instance, pass in all of the parameters, what bus it's on, what the address it is, what mux it's talking to, and what channel on the mux. So the concept of an I²C mux is we're routing the I²C connection from the machine that's running the device software to a specific peripheral. So we have a multiplexer for that. So we say, hey, multiplexer, set the channel to number 2. And on number 2, I know I have all of my Atlas sensors. So at that point, I can read from any one of those. But because not all I²C devices have unique addresses, we need to have these different channels so we can support a wide range of devices or multiple devices of the same address that have the same address. So as we look into it, we can see that it's just reading the temperature, sending some bytes onto the I2C bus, waiting a few seconds. Again, whenever you're writing a driver, it's very important to read the data sheet probably a few times to really understand it and handle all the edge cases around it. So you'll get these nice values like, oh, you want to wait 22 milliseconds. It's an arbitrary amount of time from my perspective, but from the data sheet, they've tested this and they've concluded, all right, 22 milliseconds, that's the fastest you can read from the temperature humidity sensor, just use it. And I'm sure you can dig in more if you're so curious. So once we get the read the bytes back, we can convert that to a temperature and something meaningful, check to make sure that it's within a valid range. If it's not, we're reporting none. And then we do the same on reading humidity, reading the user register. This is just a health check to say, hey, what's happening with the device, and if there's errors, it can let us know what's up. And then it can be reset. So that is the driver, and then if we open up the manager, we can see that the manager, it just initializes, it's passing in the variable names. So this is an important concept to understand, that different sensors can be used for different variables. So in the case of the SHT-25, this isn't the best example for that because it's always going to be reporting air temperature and air humidity. But if you think about another sensor, say like the Atlas temperature sensor, that is a sensor that can be put in water, it could be put in the air, it could be put in soil. So we have to ask what variables is this sensor going to be reporting on. And then in the manager, again, using these decorators to set state, we initialize the peripheral, which is basically just creating the driver. If there's any exceptions, we pass those along and debug them and transition the device into an error mode. Oh, one very important thing to know, I'm going to jump back to the driver for a minute, is the I2C module will automatically retry. So it defaults to true. And what this means is each time the I2C bus tries to either read bytes or write bytes, if it gets an error, it's going to retry. But it's going to try to do this in a semi-intelligent way where it'll back off at an exponentially increasing scale. So the first time it might wait 200 milliseconds to retry, but then the next time it might wait 600 milliseconds, and then it might wait 2 seconds. So really, if you try to read it on the I2C and you can't, if you do get an error, you can be pretty confident that there is an actual error in the I2C communication, and you don't have to handle that logic at the driver level, which helps simplify this logic greatly. So back to the manager. After it initializes and, oops, wrong manager. All right, after it initializes, sets up, and this one, no setups required. Again, this setup peripheral is where you would do something like the CO2 sensor that has a long warm-up time. The peripheral gets updated. So this update peripheral is being called from the peripheral manager class in the run normal mode. So every sampling interval, it's going to call this update peripheral function. So we define it in our SHT-25 manager to get the temperature and to read the temperature, and then we set it. So notice you don't see anything with state here, right? So I'm not saying self.state equals this temperature. I'm saying self.temperature equals temperature. And what this is doing is accessing that decorator where when I'm assigning the value of temperature to self.temperature, it's calling this temperature decorator here and setting it as a peripheral reported sensor value, and if it's not in a calibrate mode, to the environment reported sensor value. So there's the manual mode, as you've already seen, but there's also a calibrate mode. And when we're in calibrate mode, we do not want the sensors reporting to the environment because it does not reflect what's happening in the environment accurately. So imagine we're running through a pH sensor and we're putting it in different solutions. We don't want the environment data packet that we're generating from this device to be corrupted by our calibration. And I think that's about it for the SHT-25 manager. Maybe a quick note on how I start building drivers. Every time I start one, I will go to the scripts directory, and I will interact through bash. I find this is the easiest, most reliable way to get to the known good state the fastest. So if I open up read temperature.sh, you can see I'm making sure my device is I2C enabled, and then I'm using the built-in I2C commands to set a few bytes. Again, I'm waiting for the sensor to process, and then I'm reading the bytes back, converting them into a temperature, and just displaying them to the console. The same thing is true for humidity, but I think you get the point. So once I have my known good, then I start and edit the driver, and then from the driver, I edit the manager, and of course along the way, oh, what did I just do? Okay, here we are. Now we're back. Of course, along the way, you want to edit the things like exceptions to make them specific to the driver. So whether it's have an initialization error or a read temperature error, I find the more specific these are, the quicker I can figure out what the error is, and the easier it is for people to see what's actually going on in the software. So the next point is setups. And for something like the SHT25, the setup file isn't all that important, because there's only one of them, right? There's only one type of SHT25. You're not going to set it up in a different way. So to see, I guess just to see what the setup file is doing, just at a baseline level, this module name and this class name is how the coordinator manager knows how to create the instance of this sensor. Also, there's the parameters that are required to set it up, so we need to know a little bit about the variables we're using, and whether our temperature in Celsius is for air temperature in Celsius or it'd be for water temperature in Celsius. Again, doesn't make sense for this specific sensor, but for the general case of all sensors, this is something important to have. Again, it sets the communication, so for all the I2C bus, MUX, channel address, etc. And back in the peripherals tab, you saw the automatically generated peripherals cards with configurable buttons. This events region of the setup file is where you define that behavior. So this reset, shutdown, and set sampling interval is the reason that the SHT25 shows these specific events. And then also importantly, you need to specify the events file. Of course, in this one though, I haven't changed or added any more events than from the peripheral parent class, so I don't actually need to define it. I'm just using the one from the parent class. It's a bit complicated, but this will make sense as we look into another the actuator, a light panel that has multiple setup files. And finally, there's this info section. This really isn't being used by any of the code. It's really just a building for the future to say, all right, imagine there's a time where we're able to build configuration files via a user interface, and we're trying to define, what sensors would be perfect for our system? How accurate do they need to be, or what's their range? So this is what this info section is doing. But again, this isn't a critical element to the code base at this time. So for showing you the multiple setup files, let's go to the actuator with the PCF. No, sorry, let's go to the LED. That one's a bit better. So if we go to the setups, we see there's multiple setups. So there's the Libra, and there's the Taurus. I like to name different light panels that have different spectrums after constellations. It just seems fitting. So the main difference between these two light panels is their channel configuration. So on the Libra panel, there's 6 different channels. However, there's multiple channels repeated. So there's really only there's 3 unique types of channels. So there's red, cool, white, and blue. Versus on the Taurus light panel, there are 6 unique types of light, and as a result, we can render a wider range of spectrums. However, we can't hit as high of intensity around the red and cool white spectrums as we would on the Libra. So lots of trade-offs between choosing a light panel. The other information you're seeing here is some of the measurements taken to calibrate the light panel, to make sure that all the math, the linear algebra that we're doing is rooted in some experimental reality. And you can also see the spectrums associated with each channel type. Again, if you want to see more about how the light panel is doing all that math to compute to solve for the channel output percentages, to render the spectrum and intensity, there is a document on that. So that is probably all I need to say about the peripherals, aside from actually writing one. I think that'll be the next most valuable thing to do to understand what happens. And then if we go to the go to the controller, these are all basically the same exact concept as peripherals, just for controllers. And we don't have too many that we want to show you right now, but the main idea is controllers are going to route peripheral, like sensor reported values, to actuators and tell them whether they should be on or off. So if we wanted, we might as well just jump into it. So right now, if we have something like a hysteretic controller, you can see that there's different desired output percentages for the actuator. We can see the current sensor value, the desired sensor value, and based on what our controller configurations say, we know when to turn on a specific actuator or when to turn off a specific actuator. And this will get fleshed out more as we have more controllers added to the system. So there will be a PID controller, probably a fuzzy logic controller, and a few more. So the rest of these modules are fairly straightforward. Probably don't need to go too in depth onto them. There's the network. If we open this one, the main things that this is doing is checking if we are connected to the internet, getting our Wi-Fi SSIDs, so the names of the Wi-Fi networks around us, getting our current IP address, and managing access points. So on the Raspberry Pi, the Wi-Fi access point is not always enabled, and it needs to be toggled back and forth between able to let someone log into the device via the access point, or having the Raspberry Pi be able to access the network. So there's a lot of toggling going on. The BeagleBone is really nice for this because the access point is always on and it's always able to access the network. So if you want to look more into what this is doing, it's basically just managing when we connect, trying to connect, and managing all of our network interactions. So then once we know we're connected to the network, the IoT manager becomes a bit more relevant. And this is trying to connect to the cloud IoT manager, or trying to connect to the cloud IoT system. So basically, once the network is connected, the device gets registered to the cloud, it creates a key, and with a verification code, then you can go into the cloud user interface and enter that verification code that will associate your specific device with your cloud account, so that the device will report its data into your files, and you'll be the owner of those files. So that's mostly for IoT. You can see the verification codes I've been talking about. Also, this handles all outgoing and incoming messages. So when we want to set a recipe from the cloud user interface, the IoT manager is what handles that. Finally, I guess there's the resource. The resource we don't have to go into. It's really just looking at if there's too little disk space available, and if it is, going through and deleting some data locally on the database, or deleting image files, because if the device continues to run and just fills up space continuously, it eventually will crash and we will all be very unhappy, and we don't want to be unhappy. So let's go to the recipe. What this is doing is, maybe we should show the events on this one, because they're a bit more interesting. Basically, for recipes, you can start, stop, and load them. So if we go to our file, we'll be able to see that down towards the bottom. But what the recipe is doing is, once we do have a recipe started, we end up into this normal mode. Let me find that. Run normal mode, and what this is doing is it's periodically updating the recipe environment. So this translates the desired set points from a recipe file and then puts it into the shared state for the controllers to look at. And once the controllers say, all right, I see a desired sensor value, and they can look at the sensor and say, all right, I see this reported sensor value, they realize there's a discrepancy, they can set a desired actuator value to turn on or turn off, and all this is happening in the shared state. So simultaneously, the sensor is reporting values, the recipe manager is reporting desired values, and the actuator is listening for new commands, or looking for new desired states that it can be in, and based on all of these managers working in conjunction, we are able to create this control loop to control our peripherals and have them follow the desired recipe environment conditions. There's a couple other little features like pausing the recipe, stopping the recipe, starting the recipe sometime in the future, so running in a queued mode, etc. So I think that is all that this video should cover for diving into some more depth on the device side of things, and that is where I will end it.